Good afternoon, and thank you for the introduction. So my thesis, I'm doing my thesis in the UTL group within the electronic department of this university, and it's about packaging these kind of devices that Yuma has talked about. So what is the? So left and right?
Yeah.
Yeah. Okay. So the thing is, we need to send things to space because we are getting all this technology to a satellite, and the thing is, we have to package the device. The package has to allow all the signals to go in and out from the components. This means that the package will limit the bandwidth of the device. The amount of interconnections is the size of the device, and the package is limited. And the thing is, the power consumption is also determined by the energy that the device is using, and all this energy has to be dissipated by the package. And also, we need a little bit of radiation isolation from the space environment, since radiation is a harsh environment. Also, we can talk about in the introduction of the signal domains we are using. We use this device for remote sensing, for example, for signals from the atmosphere. We can do some measurement of the microwave background from the space. We will need also high-speed communications to communicate with the Earth. And we'll have to do also some onboard processing and power distribution to the chip. So the thing is, our device will be a...
Sergio, may I ask you to stay and use the micro?
Yeah, right.
Yes, there.
So we're planning to do radiometry, okay?
One more instead.
I can stay. Thank you. So we're planning to do terahertz radiometry. This means to get this kind of signals that are flying from the space. We're pointing some antenna, and we're measuring the radiation. There are actual devices already out of the space measuring this radiation. For example, here we can see 3 examples measuring the cosmic microwave background. So we'll know this microwave coming from the Big Bang. So the thing is, these are quite bulky devices. You can see like a few square meters per area. They are weight in like tons, and they are really power hungry. So the thing is, we need to stay within the constraints of size, mass, and power, because we want to package in a smaller satellite. So the thing is, our components have to be miniaturized. We have to decrease as possible the mass of the cables and everything that we can remove. And the thing is, we have to launch to space. This means that a smaller mass will have like smaller force, because force is mass times acceleration. And we also need something that consumes very little power. Our group is proposing this photonic solution. So a photonic solution is just a chip that will perform similar things as the other devices that they were larger and bigger. So a photonic chip is just a small chip, something we will see later, that integrates all the functionality, has very little amount of mass. We will replace many cables by optical interconnections, and these kind of terahertz interconnections our colleague presented. And the thing is that photonic processing is not that power hungry as electronics. So the thing is, the photonic payload that we are presenting is a hybrid combination of devices. Sorry for the short. We have PCBs, that is the control electronics that will handle all the device. We have also some other chips made of silicon, indium phosphide, and thin film lithium niobate that will perform the functionality. These are different technologies. They cannot be on the same board, so we'll have to package them together. And the thing is, they will have interconnections that will be copper, the control electronic with the other chips. We will have some data buses that is still cables, and we'll have some coplanar waveguides, that they will transfer the high-speed information through these cables. But the most of the, let's say, information will be optical or terahertz. So in the indium phosphide chip, we will perform the lasers, because we need indium phosphide to produce lasers, and the thin film niobate will detect the terahertz signal. So Actually, a PIC is a photonic integrated circuit. This is a full workbench inside a chip. So we're reducing something huge to a very, very small, tiny device. But there's a small problem. The problem is that you have to interface that chip. So you have to connect the things to the chip. All the same amount of, I don't know, whatever is there, you have to arrive inside the chip to that. So you have optical ports, you have DC ports for powering, you have databases, you have still the high-speed interconnection, and onto that, you have to consider that you have the terahertz antenna that will act as receiver or emitter. So the thing is, we will have a few signals within the package, optical, terahertz, and electrical. So optical, ultra-fast transmission and processing, can be Fourier space or guide through waveguides, terahertz, high-speed intercommunications with these kind of devices you heard just now, and yeah, an electrical for I will be quick. This is our setup. There is a laser, a modulator, and a detector. Okay, now the things we made in the lab. We have measured commercial lasers. Since the commercial lasers are controlled by different variables, we have to measure the thing, and we have to find the way to continue tune the lasers. This is a little easy compared with your things, but we made like an algorithm to do that. We also have simulated lasers and design lasers, and with ring resonators and match-sender interferometers, we also have design filters and modulators. So the thing is, we are talking also about terahertz. We have the radiometer chip that is interfaced with the optical ports, and we also use the LIPWAVE technology as emission for the terahertz radiation. So in the last picture of the right, you can see a actual photonic chip that is performing terahertz detection. With this antenna is around 1,000 euros, now that you ask. So this thing green on the right is 1,000 euros or 1,200 euros. So this is what we're going to remove from the system, but now it's being given the energy to the chip. So another thing we did was a terahertz measurement setup for the 3D radiation pattern of this kind of devices. So here we have the LIP emitter with some testing dielectric antenna, in this case an array of silicon. And we can measure this radiation pattern out of the emission with this setup. So actually we are measuring all around, scanning, and then we can measure and generate these kind of patterns to really know where are we sending all this radiation, or where do we have to look to get the radiation to the chip. This is a reflector, a chip version that is compatible with this LIP4 thing, so we can use it as a telescope for terahertz radiation. Since we also need optical interconnections, there are our group has acquired a new 3D printing machine, a micro printer called Nanoscribe, and we can design lenses, print lenses on chips, and do chips with lenses integrated. Since I'm also interested in performing computation within the package, I also have designed. We also have designed some functional chips, optical, that can be printed, that can be 3D printed. In this case, it's an match-sender interferometer. So we can perform some analogically computations within the chip. For example, an interferometer, we can detect things that can be separated with interferometry, whatever. Yeah, so we did simulations, fabrications, and we have measured these devices for interconnection. So to learn all these things, I had to attend a few courses about PIC, so Photonic Integrated Circuits Test and Design, JPICS in Eindhoven, Tyndall in Cork, BLC in Valencia about the same topic, and CMAX design here in this university. And then I got all the knowledge to write and do all these things. So there are some achievements here, a journal paper about bandpass filter in the optical domain, some conferences about photonic design and filterings also, and terahertz detection, and yeah. So that was it. Thank you very much for your attention, and questions are welcome.